Okay, welcome back to Math 107 Pre-Calculus. Today we're at Lecture 2, and today we hope to cover 3 sections. The first one being Section 2.3, the graphs of functions. And let me just open to page 219 and briefly show you the 2 objectives here. The objectives are to identify the graph of a function, and we actually touched on that yesterday, so that will be a 30-second exercise. And then objective 2 is to obtain information from the graph of a function, that is, given the graph, answer some questions about that graph, and then obtain information about the graph of a function. That means, given the equation for the function, what do you know about the graph of a function? So this is kind of a little fun exercise. Then we're going to move on into 2.4, talking about properties of functions. And let's look at those objectives. Now notice in this one we're only looking at objectives 3, 4, and 6. So when you're working on your homework or studying your textbook, those are the ones that we are going to focus on. And these are very useful terms in objective 3 once you get to calculus. You want to be able to look at a graph and tell where the function increases. And we're going to be looking at over what interval does the function increase, what interval does it decrease, and over what interval do we have a constant. And then, very, very useful for calculus also, is looking at a graph and locating what this book calls local maxima and local minima. In calculus, you will be using derivatives to identify local max and local min. Now, you're going to hear me say relative. Many calculus books and textbooks will use the word relative max or relative min. So once we get there, I'll be interchanging those 2 words, local and relative. And then we're going to look at average rate of change of a function, and we'll look at a couple little applications there. Average rate of change, I think we touched on that a little bit in Lecture 2. Okay, and then I hope that we get to 2.5 today. We're going to make every little effort to get there sometime. 2.5, I'll go ahead and we're going to look at objectives 1, 2, 4, and 6. And the reason I think we'll do fine there is because I think you've done this for many years. Graph a linear function. Then we want to look at some applications of linear functions. Your book has a tendency to call those models. They're applications. And we want to distinguish between linear and non-linear relations. How do you recognize linear? And then an application is direct variation, and that's a real simple application, so I think we'll do fine with that. Okay, and there's a couple terms in there that you will need for your business or liberal arts calculus class, such as revenue, cost, profit. We'll talk about break-even points, consumer demand, producer supply, all kinds of fun calculus things. Okay, so we are now ready to start with section 2.3, but before we do, we've spent 2 lectures now on functions. Tell me something you remember about functions right off.
Y equals f of x.
Okay, so we can define y as being a function evaluated at x. Okay, what'd you learn?
The value of functions.
To find the value of a function, that means what is the y value given x is such and such. Excellent. What'd you learn?
The difference quotient.
The difference quotient. Okay, that is an application that you're going to be using in your calculus. When the difference quotient, who knows what it is? F of what?
Isn't it the slope of the secant line?
It is the slope of the secant line. What's the secant line to a curve?
F of x plus h minus f of x over h.
Okay, that's the formula for the difference quotient, which gives you the slope of a secant line. A visual and in words, what is a secant line to a curve?
It's a line that passes through any 2 points on a curve.
Okay, a line that passes through any 2 points on the curve. That is exactly what a secant line is, and the difference quotient ends up just being the slope of the line between any 2 points. Perfect. What'd you learn?
For each x, there can only be one y
answer?
Okay, in order for a relation to be a function, for each x, you only get one choice of y values. I'm not sure we learned anything else. Did you learn anything else?
I guess you guys covered it all.
You think we did?
Yeah.
What do you think?
I was going to say functional relation.
Functions and relations. Okay, all right, excellent. Great. We're now experts. Oh, domains. Didn't we talk about domains too? Yeah. Domains is those values for x that make the functional value y be a real number. Okay, and we have restrictions when we have division by 0 or a negative under the square root. Remember that? Okay, so domain is all those values of x, all those real numbers for x that will make y be a real number also, or be defined. Okay, so we are good, good, good. Okay, we're ready to start in 2-3, the graph of a function, and as always, because I think it's a good idea, we need to make sure that our algebra is good. So we're going to return to the back of 2.3, preparing for this section, and we have a couple questions. They should go pretty fast, and I will read them to you. So, the first one. The intercepts of this equation are, let's do this orally together. What's it asking for when it says the intercepts? What are you looking for? What does it mean, intercepts?
X and Y.
The x-intercept and the y-intercept. So when you have a graph, you want to know, does it cross the x-axis? That's called an x-intercept. And if it crosses the y-axis, it's called a y-intercept. Okay, how do you know how to find where it crosses the x-axis? What do you do? How do you figure? Where does it cross the x-axis? In general, how do you find it?
Do you set Y to 0?
Exactly. If you're on the x-axis, the y value has to be 0. So if y is 0, what's x here?
4.
4, what else?
Negative 4.
4 or negative 4. If you let y be 0, that term disappears and you have x squared equals 16. So x is equal to 4 or negative 4. As you're answering these, I'm going to do a quick sketch that's not perfect. Okay, I'm just plotting on my x-axis 4 and negative 4. Okay, how do you find your y-intercept? Set x equal to 0, so you'll now be solving 4y squared equals 16. Y squared is equal to 4. Y is equal to plus or minus 2. Who knew right off what the graph of this equation is? Anybody know? Do you recognize it?
It's like a parabola.
A parabola would have a x to the first with a y squared. Okay, what else might it be? It's got an x squared and a y squared in there. Recognize that as anything? Where's all my geometry folks?
Asleep.
Asleep? All right, this would be an ellipse. I'm just going to show you. You knew that, right? You just didn't tell me?
I knew that.
All right, this is the graph of an ellipse that looks like this. Okay, so that's the graph of an ellipse. You didn't have to know that. You just had to be able to find the intercepts. Would you say that this equation that we just worked with represents a function?
No.
No, why not?
It isn't. Each x has 2 y's.
For each x value, well, all of them except negative 4 and 4. For all x between negative 4 and 4, you have 2 choices for y, and you were wanting to tell, one of you were wanting to tell me it doesn't pass the vertical line test. Didn't we mention that yesterday? For each x, there can only be one choice for y. So this is a relation. It's an important relation, but it's not a function because for each x, there are 2 choices for y. Okay, everybody good on that? X and y intercepts. To find the x-intercept, remember the y value is equal to 0, solve for x. For the y-intercept, all the values for x are equal to 0 and solve for y. Okay, let's go to our next are you prepared question. True or false? Give you a second to work this one out. The point -2, -6 is on the graph of the equation x equals 2y minus 2. The point -26 is on the graph of the equation. How many say true? Oh, you hadn't had time to do it yet. Sorry.
We haven't.
Okay, if you don't have it, you're working too hard. How many say true? How many say false? That must mean the rest of you are working too hard. Okay, the question is this point, -2, -6, on the graph of this equation? What's the graph of this, by the way? What would that be the graph of? It's got an x to the first and a y to the first.
It's a linear.
It's going to be the graph of a line. That's not normally the way you look at it. You usually look at y equals mx plus b, but you still have an x to the first and a y to the first, so it's the graph of a line. So how do you determine if this point is on this line? Just do a little substitution, and I'm going to do like this. I like to do a little t deal where x is -2, so this side is x at -2, and now I'm going to substitute in -6 for y and see if it matches. 2 times -6 is -12. -12 minus 2 is -14. And so this point is not on the graph of that equation. Okay, so you're just checking. I saw some of you sitting there trying to graph it, and then you were going to look. Well, you could graph it, but the question was, is this point on there? And if it's on there, then this has to be a true statement when you substitute it in. Everybody good? Okay. So we're all warmed up. We're now ready for section 2.3, and objective 1 we've already mastered, and then we'll move into objective 2. Objective 1 was simply look at the graph of a function and determine, or the graph, and determine if something is a function. And I'm on page 220, and this is the vertical line test that you have already told me about. This is how you can look at a picture of a graph and determine if it's a function. Vertical line test. A set of points in the xy plane is the graph of a function if and only if. That means both sides of this sentence have to be true. If every vertical line intersects the graph in at most 1 point. In at most 1 point. Okay, so they gave you a couple of little pictures here that are showing it right off. This is the graph of y equals x squared, and you keep going back to the definition of a function. For each value of x, there's only one choice of y. The vertical line test will tell you that for each value of x, going through the x-axis, there's only one choice of y. Same thing for the graph of y equals x cubed. Here's the graph of x equals y squared. When the vertical line went through x at 1, you had two choices for y. And then D is the graph of a circle, x squared plus y squared equals 1. That's a circle. We just looked at the graph of an ellipse. For it to be a circle, the coefficient in front of the x squared and the y squared have to be the same. Whenever the coefficient in front of the x squared and the y squared are different, then you're going to have an ellipse. Okay, so this is a circle. And it does not represent a function because for each choice of value of x, you get two choices for y. I told you that'd be a 5-second exercise, right? Okay, so now what we want to do is, and I thought the examples in the book were really the very best for going over this. So we're going to go to the exercises. And the first thing we're going to do is be given a graph. We're looking at page 224. And a lot of this is just making sure that we're communicating the words, what does the symbols mean. It's just pure communication. So we're going to look at problem number 10 on page 224. Is that good? Problem number 10 on 224. So communication is our big objective here. What is the question asking, and then how do we look at the graph and answer the question? All right, so in number 10, this is the graph of a function that's given. The graph of a function. How can I look at that and tell that's a function without them telling me? Passes the vertical line test. No matter where I draw a vertical line, I get for each x only one choice for y. Okay, part A says find f at 0. What is that asking me in words?
What is
When
the
x is equal to 0.
When x is equal to 0, tell me the
y value.
y value. Okay, so when x is equal to 0, what is the y value here?
0.
0. The next one, f evaluated at 6. When the x value is 6, what is the y value? And everybody says
0.
0. What did I just get off this curve? What's another word for that? What did I just find?
Y.
I found the y values, but they're touching the x-axis here. What do we also call that?
The x-intercept.
X-intercepts. That was, my question was vague, wasn't it? I was trying to get
Yeah.
out of you x-intercepts. All right,
It's like
so I just found two x-intercepts. There's also an x-intercept here at 4. Okay, x-intercept. 0, 0, also there's a y-intercept. So 0, 0 is the x-intercept and y-intercept. Okay, let's find f of 2. These almost sound too easy, don't they? What is f of 2? Just yell it out.
negative 2?
Negative 2. What's f of negative 2?
1.
1.
1. Is f of 3 positive or negative? Is f of 3 positive or negative? What do you say?
Negative.
Negative. 3 should be somewhere right here, and this says, is the y value positive or negative? Okay, and another, we could say something like f of 3, I don't know if you can see my pencil, is less than 0. Isn't that true? If f of 3, that's a negative y value, a negative number is less than 0. Just working on a few symbols. Everybody good? Okay, is f of negative 1 positive or negative? F of negative 1
Positive.
positive. That's up here. Okay, for what numbers of x? And a lot of times I'll say for what values of x instead of numbers. What values of x, numbers of x, is f of x equal to 0? Translate that to words for me.
For what x values is y equal to 0.
For what x values is y equal to 0? So where is y equal to 0?
0, 4, and 6.
0, where?
4.
4 and
6.
6. Everybody got it? Okay. For what numbers or values of x is f of x less than 0? For what numbers of x is f of x less than 0?
Greater than 0 and less than 4.
Okay, so we're agreeing that between 0 and 4, all the y values are negative. How do you write that in interval notation?
So parentheses 0,
Parentheses 0,
4,
comma, 4. Why am I using parentheses and not a square bracket?
because it's open.
Okay, at 0 and 4, the function equals 0. So if I did a square bracket, I'd have to be claiming that at 0, the y value was less than 0. Everybody got it? Okay. All right, so I'm not hearing from every single person, so you two ladies over here, what is my domain of f? What's my domain? Domain.
It's your, like, isn't that the common,
When you think of domain, what?
yeah, like
The real numbers, x of the real numbers.
Okay, and so which real numbers in terms of x are covered here? It doesn't go for all real numbers because you got little solid dots here. So what range, what interval do you see for the domain? What's the smallest x value on our graph?
-4.
-4, and the largest x value is 6. So our domain is that -4. Is that going to be a square bracket or an open parenthesis? Bracket, because the -4 is included, comma, and we're going to go all the way up to 6 with a square bracket. That's my domain. Okay, I'm going to get these two guys on the second row here. Tell me what your range is. Range.
Is it 2 and 0?
2 and 0. Are you looking at y values?
Yeah.
What's your smallest y value?
-2.
-2. And what's your largest y value?
5.
That's an x.
Or number 3.
-2 to 3. So your range then is looking at your y values, and your y values go from -2. Are we going to use a square bracket or open parenthesis? Square.
Bracket.
Because -2 is there, and we're going all the way up to 3. Got it? Okay. We already said what the x-intercept is, which is 0, 4, and 6. The y-intercept we've already said is 0. How often does the line y equal -1 intersect the graph? All right, first of all, let's play Sesame Street. Use your fingers. What does the graph of y equal -1 look like? What's the graph of y equals
It's a
negative?
straight line.
Yes, it's a horizontal line. Okay, so we're going to go down here and guess where we think y equals -1 is. And so y equal -1 goes like this. Because every point on this line would have y equal to -1. Does everybody see that? So the question is, how often does this line intersect the graph? And everybody in unison says? Twice. Okay, let's play Sesame Street again. What does the line x equal to 1 look like? Everybody's finger in the air. What is it? X equal 1? You guys don't have your fingers in the air. Okay, that's called a vertical line. X equal 1. So we're going to come up here and find x equal to 1. And we draw a vertical line. This is x equal to 1. This one was y equal -1 down here. X equal to 1. Every point on this line would have an x value equal to 1. Well, you already knew the answer to this because you'd already told me this was a function because it passed the vertical line test, right? Vertical lines. All right, so for each x value, you only had one choice for y. So how many times does it intersect the graph? Everybody says 1. Okay, M, for what value of x does f of x equal 3? All right, give me in just plain old words, what is that asking me for?
Oh, for what value of x does y equal 3?
Yeah, so you're going to look for where is y3 and give me the y value, because remember, y is a function of x. So when y is 3, find x. Okay, so here's y at 3 up here. And what's the x value? 5. Does everybody see that? F of 5 equals 3. When y is 3, the only x value we have there is 5. Everybody got it? Okay, for what value of x does f of x equal -2? 2. When y equals -2, the only x value we have here is +2. Everybody good? All right, we're going to check you off there and say you are indeed an expert. Let's look at number 20. Okay, that was we were given a graph and we were asked some information. Number 20, which is the next page, 225, we are also asked a couple questions. And I think everybody's going to do great. So I'll ask the questions and you look at the picture. The first question is, looking at this, I'm going to ask you first, how do you know this represents a function? Everybody says vertical line test. Okay, let's go with what is the domain. I'm going to start with you ladies again to give you a chance to quickly tell me, what is the domain of this function?
Negative 3 and 3.
To infinity, right?
Infinity.
Negative 3 to infinity. How would you write your domain? How do you write that in interval notation?
Bracket,
Square bracket,
negative 3, infinity,
and what do you put after infinity?
Parentheses.
Parenthesis. So we have all the x values covered from negative 3 on forever, never, 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 never. Okay, give you a chance to tell me here your range. What is your range here?
Bracket 0
Bracket 0
to infinity.
to infinity. Because this curve is just going to go this way forever, never, never, so it's never going to reach infinity. Okay? Tell me the x-intercepts, you guys back here. What's my x-intercepts?
Negative 3 and 2.
Negative 3 and 2. And you two tell me your y-intercept.
2,
2 is your only y-intercept. If you have a function, how many y-intercepts can you have anyway? If you have a function,
Oh.
you can only have one, right? Perfect. All right, so we're expert at number 20. Now we're going to jump on that. Both of these were given the picture, the two examples we just did, given the picture, answer some questions. Okay, now the other part of that objective is given the equation, this is number 28, answer some questions about the graph without seeing the picture. Okay, so those were our two objectives there. Given the picture, answer questions. Now given the equation, answer some questions about it. All right, we're going to first say how you do it, and then we'll do it. This is the function f of x equals 2x over x minus 2. The first question is this point on the graph? And I do not want to sit here and sketch this at the moment, although we're going to learn to sketch this in about 3 sections. But how do you determine if this point is indeed on that graph? What do?
Plug in.
Substitute in. All right, check your arithmetic. Everybody go for it. And we're going to take a vote and see if it's on there. Okay, let's see what you got here. Oops. All right, this is the function, and we wanted to know when x is equal to a half, is the y value negative 2/3? So was this everybody's first step? All right, so now remember, whenever you're trying to show something, you need to work on one side of the equation and bring it down to see if it'll match the other side. So we know 2 times a half is 1. And then 1/2 minus 2 is negative 1/2, which is a negative 3/2, right? 1/2 minus 4/2 if you wanted to get common denominators. And and remind me from yesterday, what kind of fraction is this right here? Complex or compound, good. And so we got 1 divided by minus 3/2, so what do? invert and multiply, 1 divided by. So you invert and multiply. And so 1 times negative 2/3 is negative 2/3. So we have verified that the point 1/2 negative 2/3 is a point on the graph of this function. Everybody good? Okay, let's go to question B. If x equals 4, what is f of x? What are you going to do, everybody? If x is 4, what is the value of the function at that particular x? What do you do?
Just substitute 4.
Just substitute 4 in. So take about 3 seconds and tell me what that is.
4.
Wait, yeah, 4.
Okay,
I did
so
that.
4 times 2 is 8. The numerator is 8. The denominator is 4 minus 2. So 8 divided by 2 is 4. All right, so when x is 4, the y value is 4. So the question then is, what's a point on the graph? And everybody says 4, 4. The ordered pair 4, 4 is the point on the graph. Okay, if f of x is 1, what is x? What is it? If x is 1, oh, I was doing it wrong myself.
I was like,
I
why
was
do you want
going-
an answer that fast?
I was going, why in the world is it taking y'all so long? That's an easy number. All right, maybe I better write that one out. Okay, f of x equals 2x over x minus 2. And it says f of x is equal to 1. And it says, so what is x? So where'd you put the 1, everybody?
In the f of x.
In the f of x spot, which is not what I did in my brain because I was
Yeah,
wondering what was
like-
taking y'all so long. It says solve for x. So we have 1 equals 2x over x minus 2. How are you going to solve this equation? We did one of those yesterday.
Multiply by x minus 2.
Okay, remember you multiply through by the common denominator. Okay, do unto one side of the equation as you do unto the other. And that common denominator is x minus 2. Okay, denominator on the left is 1. The denominator on the right is x minus 2. So the common denominator of both sides is x minus 2. Okay, so 1 times x minus 2 is x minus 2 equals. Now we're going to multiply this out and we get, oops, no we're not. That divides out,
Yeah.
gives us 2x. X minus 2 divided by x minus 2 is 1.
Yeah.
All right, now we're going to solve for x, so let's subtract x from both sides. Negative 2 equals x. I subtracted 1x from both sides. Everybody with me? Okay, everybody looks like they have happy faces. All right, so f then of negative 2 is equal to 1. You can double check that. Put negative 2 in, you will get negative 4 over negative 4, negative 2 minus 2. Negative 4 over negative 4 is 1. Okay, everybody good? Okay, what point or points are on the graph of f from this? What's the point here? How do you write it as an ordered pair? Negative 2, 1. These sound like trick questions. They're so easy, right? Okay. Let's go back to D. What is the domain of this function? This is called a rational function because it has a fraction and the numerator and denominator are polynomials. Okay, it's a rational function. What's the domain of this function? 3-second question.
All real.
Except
Or 2.
all reals except for 2. Why can 2 not be part of the domain?
Just can't divide by 0.
Can't divide by 0. Okay, E, list the x-intercepts, if any. X-intercepts. I tell you what, let's divide up and not work so hard. This side of the room do x-intercepts. This side of the room do y-intercepts, and then we'll do both of them. Okay, you guys get the x-intercepts, you get the y-intercepts. This one's going to sound like a trick question, too.
We're doing the what?
I think you're doing the x.
Yeah, we're doing that.
You're doing x and you're doing y. Don't confuse me. I can't remember what I tell you to do. All right. What's your first step for looking for an x-intercept?
Multiply, well,
What are you going to
set y equal to 0.
set y equal to 0?
Yeah.
Okay. Let's flip this page over. So if we're looking for the x-intercept, we let y be 0. You let y equal 0. Okay, now what would you do?
Multiply by x.
You multiply by x minus 2, both sides. So we get 0 equals 2x, so x is equal to 0. So it tells me I've already figured everything else out. When y is 0, x has got to be 0. And what did y'all find for the y-intercept?
Same thing.
You had to find the same thing, right? For the y-intercept, you let x equal 0. So you basically have y equals 2 times 0 over 0 minus 2. So 0 divided by negative 2 is 0. But actually, if you'd found the x-intercept along with them, you would have known right away the y-intercept was also 0. Everybody good? X and y-intercepts?
Yeah.
Okay. Now we're flipping the page to 226. And we're going to go down to the discussion questions. All right, and we've already talked about 33, how you find a domain and range. Remember, a domain is you're looking for what x values are covered, and the range, what y values are covered. Okay, number 34. This is under the discussion and writing. How many x-intercepts can the graph of a function have? How many x-intercepts can a function have? Right, it can have a ton of them, right? It doesn't matter. It could have a zillion of them. And in fact, if you have the line y equal to 0, that is your x-axis, right? Y equal to 0 is the x-axis. So you have an infinite number of x-intercepts on the line y equals 0. So an x-intercept can, a function can have a zillion x-intercepts. Okay, how many y-intercepts can a graph of a function have? One, because it's got to pass that vertical line test. All right, here's a trick question, kind of tricky. Is a graph that consists of a single point the graph of a function?
Well,
Let's get a visual of what it's saying.
the function value.
I'm just going to plot a point here and call it 2, 5. Why?
It is.
Your answer is correct.
Yeah.
The answer is yes. Why is that the graph of a function?
It has the vertical line.
It does. It passes the vertical line test. For where your function is, which just happens to be at one point, there is only one choice for y. So that one's kind of a tricky question, but a point can be a function. All right, let's see if we can write the equation for this function that turns out to be a point. All right, so functions usually start out as f of x equals. So what would you say? F of x equals, what does f of x equal?
2, 5.
Remember, y is that
Easy.
function of x. What is
So it's
y?
2.
5.
5.
So y is equal to 5 only when you have a restricted domain and x can only be equal to 2. So here's how you would write your function for a point. The function is 5, y equals 5, but we're having a restricted domain only when x is equal to 2. If you didn't have that restriction, what would the graph of y equal 5 look like?
The horizontal line.
It would be the horizontal line going through y equals 5. Correct?
Mm-hmm.
Okay, perfect, perfect, perfect. All right, the next thing we want to do is number 38. This is just kind of looking at a graph and see which ones sort of go with these words. Are we going to be able to get them all on there? There we go. Okay. All right, so these pictures represent some application, and we're going to be eventually doing some applications, and we want to see which graph we think makes sense. Sometimes if you don't know some, you go through a process of elimination, right, and you knock out some. Okay, the temperature of a bowl of soup as a function of time. All right, when you say function of time, that means the x-axis has to be time, and the y-axis has to be the temperature of a bowl of soup. We're going to assume that bowl of soup is going to, it comes off the oven and it's hot, so what's going to happen to the temperature? Go down. So which one of these do you think looks like a graph that might represent the temperature going down of a bowl of soup? All right, and what's going to happen is and this is taking you into logistic equations, which you're not studying, but this is going to have to level off. Where is the temperature of your soup going to approach? It's going to have to approach the room temperature, right? So when you take your soup in here, it can never get colder than what's in the room. So this is an exponential function that's going to level off to whatever the temperature of the room is. Okay, good. All right, B, the number of hours of daylight per day, over a 2-year period. So along the x-axis, we're having 2-year periods over daylight per day, and the number of hours, that is your y value, the number of hours of daylight over a per day period for 2 years. Which one looks like it's going to plot your number of daylight hours every day over 2 years? It looks like the fifth one, right? Because you got your daylight hours and then you don't have so many. Remember your shortest day is in December and June is your longest, right? Okay. C, the population of Florida as a function of time. Now we're assuming, you have to make some assumptions here, that there's been no hurricanes, no disease or anything like this, and this is the ideal situation. What do you expect to happen when you got population growth? You expect it to grow exponentially? All right, so we're going to assume nothing's happened in Florida. Okay, everybody's healthy and reproducing. All right, the distance a car traveling at a constant velocity as a function of time. Okay, so the car is on cruise control, and a function of time along the x-axis is your time, along your y-axis is your distance, and you're on cruise control. Which one's going to look like that? 3. You're at a constant velocity because your distance is just, if you're on 60 miles per hour, at the end of every hour, you've gone up 60. Okay. And I can tell you the reason this problem E is in here is your author of the textbook loves golf. I met him this summer and he loves to play golf. The height of a golf ball hit with a 7-iron as a function of time. Which one's going to look like the height of a golf ball?
The only one we haven't said.
The only one we haven't picked, right. You start out with a height of 0, you hit it, it's going to hit its max, and then it's going to come back down. Okay? All right. Let's look at number 42. Number 42. The x-axis is going to represent time in minutes. The y-axis this time is representing speed or velocity in miles per hour. This is just the speed of your car. So it's going to be minutes versus your speed. Okay, minutes versus your speed. Okay, over what interval of time, now don't forget, the y-axis represents your speed, the x-axis represents time. Over what interval of time is Michael, by the way, that's the name of your textbook, Arthur, Michael Sullivan. Okay, over what interval of time is Michael traveling the fastest? When does he have the fastest speed?
Between 7.
Okay, between 7 and 7.4. So your interval would be close bracket 7 to close bracket 7.4, right? Over what intervals of time is his speed 0?
4.26.
Okay, we got 0 speed on the interval from 4.2 to 6, correct? Because the y value is the speed.
9.1 and 0.
No,
Oh,
that
just
speed
once the
changes,
interval is
right?
defined.
So it's only in this little interval right here the speed is 0, correct? Because at 7, the speed is 50 miles per hour, right? Okay, so only the interval here is where the speed is 0. Okay, what is Michael's speed between 0 and 2 minutes? Between
30.
30, okay, his speed increases to 30 miles per hour between 0 and 2. Does everybody see it? What's his speed between 7 and 7.4? That's a constant speed. They are 50, right? Constant speed. This was an increasing speed. This one is a constant speed. Okay. Oops, I already answered my next question almost. When is his speed constant? Where's his speed constant? When?
2.
From
4.
2 minutes to 4 minutes, he's at a constant 30 miles per hour. What else?
From 4.2 to 6.
4.2 to 6, he's at a constant 0 miles per hour.
7.
7 to 7.4, he's at 50 miles per hour. And what? 7.6 to 8, he's at 38 miles per hour. So we got constant speeds here. So from 0 to 2, he's increasing his speed. What kind of, what happened between 4 and 4.2? That was a decreasing speed, wasn't it? Decreasing speed. Okay. Everybody good? That's number 42. What else did I want to hit? I think that's it. Let's turn through the pages and make sure we've got all of section 2.3 covered with our objectives. Just going to flip through the pages. We know how to look at a graph and tell us the function. Everybody say it again. Look at the picture. What do you go with?
Vertical line test.
Vertical line test. Okay? And remember that if the vertical line intersects the graph in at most one point, it will be a function. Okay, we learn to use some symbols, and what do those words mean? F of 0 means find the y value. We know that domain means what is the intervals over x where this function is defined. Range, what is the intervals over y that this function is defined. Intercepts, where does it cross the x-axis? Where does it cross the y-axis? We also learned, given the equation, this is example 4. You want to be sure you go back and read and study your book. Example 4 is the average cost function. They're putting some application here. Average cost function. And given a function, can you answer some questions? Okay, I think we're in good shape for 2-3 unless you think I might have left something out. Anybody? Everybody good? Okay, we're going to move on to section 2.4. I'm on page 228. 228. And of course, I've already told you we're only doing objectives 3, 4, and 6. We're going to focus on the words functions increasing, decreasing, and constant. We're going to focus on the words local max, local minima, also the words relative that's not shown up in your book, and average rate of change, average rate of change. Okay, let's go preparing for the section at the end of the chapter. All right, I want you with your neighbor. Just pick a neighbor. There's enough so that everybody can pick a neighbor. And I'm going to pass out your questions. There's 5. 1, 2, 3, 4. Okay, I'll take number 5. So you ladies are number 1. Y'all are number 2. You're number 3. You're number 4. And I'll do number 5. And those watching this by video, you get to do them all. This is page 236. Everybody ready? Y'all look happy. Okay. I'm going to do what you tell me, and then everybody will unanimously say you are correct. All right, the interval 2, 5, the interval can be written as the inequality. Okay, how did you write the inequality for the interval 2, 5?
2 less than x less than 5.
How many say perfect?
Huh? Wait, what?
Is this the inequality notation for this interval notation? X is between 2 and 5.
Yeah.
Okay, so we'll give you a check plus. How's that?
Great.
Okay. All right, number 2. It says, find the slope of the line containing the points -2, 3, and 3, 8. Find the slope. What's your formula for slope?
Changing y over changing x.
Change in y values over change in x. Okay, so give me your steps so I'll write it down. What with the numerator?
3 minus negative 3 minus -2. I mean,
The difference in the y's is 3.
8 minus 3. I did it back.
8,
It
take
still
away
comes out the
3. And the difference in the x's is
3 minus -2.
3 minus -2.
It comes out the same.
Okay, so you're subtracting the y values, subtracting the x. 5 over 5. Did you get a slope of 1?
Yeah.
Okay, everybody good? Oh, you can't see. Thank you. Keep me straight. There you go. Yes. Everybody good?
Yeah.
All right, number 3. Question was, right, oh, y'all had an easy one. Gracious, that's not fair. I should have given you number 5. Write x greater than 3 using interval notation. What'd you guys do?
Bracket 3,
Bracket?
then infinity open.
Okay. What does a square bracket mean?
It's closed right there. Oh, it's both open.
Okay. If it had been or equal to,
Yeah.
it would have been square. So let's put a big old X here so you'll remember it.
That makes me
That makes you feel bad, hurts that self-esteem. All right, parentheses 3 to infinity. You only use a square bracket if it had or equal to. Okay? Good. When you miss something, even me in front of you guys, it goes to my long-term memory. Just like if you miss something, it goes to your long-term memory, and you go, yay, I'm glad I made a mistake, because now I'll never forget it. Isn't that what you just said? Yay, I made a mistake. All right, number 4. Write the point slope form of the line with slope 5 containing the point 3, -2.
This is y equals mx plus b.
All right, y equals mx plus b is not called the point slope form. This is called the
slope intercept.
slope intercept form. Okay, so let me just back up. There are 3 ways you can write the equation of a line. One's called the slope intercept. M is your slope. Your B is your y-intercept. Okay, another form of the line is just a general form. And that, who tells me what a general form is? What
It's
is
just basically your slope and your point, right?
a general form for the equation of a line? AX
Oh,
plus
C.
BY equals
C.
C. You know you have a line because you have an exponent on X is 1 and the exponent on Y is 1. Okay, but this one was a little bit tricky. It asked you for the point slope form of the line, which is one of my favorite forms. What was that?
To substitute, we put -2 equals 5 into 3.
You're exactly right. It's going to be y minus the y coordinate equals the slope times x minus the x coordinate. That's no more than the formula for slope and then cross multiplying. Change in y is y minus y1. Change in x is x minus x1. So if you just cross multiplied here, that came right from the equation for the slope. Okay, so now that we had a quick review of lines, the point we were given was what, 3, negative 2? So we'll have y minus, and in the place of y here we use a negative 2, equals, and the slope is 5, x minus 3. Is that good?
Yeah, I used the one, right? The first one that I gave you.
Okay, the first one that you gave me, the question said, though, find the point slope form.
Yeah.
And that form is called slope-intercept form. So point slope form is here. And this, it would either be this, or you might simplify and write it as y plus 2 equals 5 times x minus 3. I mean, if you did this, that is clearly the equation for the line, but since they were real picky here and asked for a particular form, they were trying to get you to review those forms. Okay, everybody good? Remember all that? Usually when I ask you on a test for something, I don't say it must be point slope, it must be general, it must be this. I'm just happy that you get it. All right, I will do number 5 with your help. Number 5 is y equals x squared minus 9, and I'm supposed to look for the intercepts. By the way, who can tell me right away what this is the graph of?
It's a parabola.
It's a parabola. Is it going to open up or down?
Up. But
Isn't it down?
It's either one of those. Which one is it?
Down.
Nope, up.
it's not negative.
You had a 50-50 chance. Since the coefficient in front of x squared is positive, it's just going to open up. Okay? All right, but the question asks for intercepts, so x-intercepts. What do I do to find the x-intercepts?
Set y equal to 0.
You let y be 0. So we'll have 0 equals x squared minus 9. X squared is equal to positive 9. What is x, everybody?
Plus or minus 3.
3 or negative 3. The other thing you could have done here, just reminding you, is you could have factored this. This is the difference of two squares. X minus 3, x plus 3. So you could have solved that direction. Or if you solve this direction, you're using that square root principle where you take the square root of both sides. X squared is 9, so x is plus or minus 3. Okay, for y-intercept, we're going to let x equal to 0. And that's an easy one. So what's my y-intercept?
Negative 9.
Negative 9. Let x be 0, y is negative 9. Okay, and just a quick graph, although you're not responsible yet. The y-intercept is negative 9. The x-intercepts are 3 and negative 3. The vertex is down there. The graph looks like this. Okay, something like that anyway. All right, good. We are now ready for section 2.4. And some of the first things we want to do, we have 1 minute. So we will take a little break and we're going to come back and we're going to do part 2 of lecture 2 in about 5 or 6 minutes. All right, so we'll stop there. Okay, we're continuing with lecture 2, so we're just going to call this lecture 2B. We didn't finish all of our topics earlier. We're in section 2.4. At the end of the last tape, we had looked at preparing for the section. So we're all prepared for section 2.4, and now we're going to look at objectives 3, 4, and 6. A lot of this has to do with vocabulary. And then we're going to move on into section 2.5, I hope, linear functions and their applications. All right, so for lecture 2B, we're going to work on some vocabulary. And I drew a graph for us. This is the graph of some function, f of x. And along the x-axis, my units are by 1. And along the y-axis, my units are by 1 also. Alrighty, so I've looked ahead. I know what the vocabulary words are. So, one of the things that we want to talk about is where the functions increase. Over what interval does the function increase? And when you're looking for increasing, basically it's saying as x gets bigger, the function increases, the value of the function, that's the y values, right? So as x gets bigger, if we want our function values to increase, that means the y values have to get bigger. Okay, so if we start from left and we're going in the direction of to right, what would you say about the curve coming from these? This just goes down forever and ever and ever. Okay, what kind of function would you have here? Would this be what you would say is increasing or decreasing? Increasing, because you're starting over here with x and you've got some negative y value. And as you move, like as x is coming along this way, your y values are getting bigger. So the interval here where x is increasing is from what, negative infinity to negative 2? All right, and at negative 2, we wouldn't say that was increasing or decreasing, right? And then as we leave negative 2, what would you say about the function? Decreases till you get to about where? All right, these are units of 1, so this looks like it's about at a negative a half, right? Because let's write this in here. So we're increasing. This would be from negative infinity up to negative 2, because you're measuring with respect to x. You're giving it over the interval for x. Then you just told me it was decreasing, starting at negative 2, going, these are values for x, till we get to somewhere about a negative 1/2. And then what happens after x at a half? Increases until it gets to, and my drawing's not so perfect, that looks like about 3/2 here, halfway. So we use a little symbol like union. That means it also is going to increase here. So it increases starting at negative 1/2, going maybe to 3/2. And then tell me what else. What's the next thing I need to say? Decreases till it gets to 4. So we'll say also it's decreasing from 3/2 to 4. And then what happens? 4 to, so it increases again from 4 to 5. And then what? Decreases from 5 to infinity. Okay? So basically, whenever you have positive looking slopes, your function is increasing. And when you have negative looking slopes, your function is decreasing. All right, let's look at what the book, how the book defines this. I'm on page 231, page 231 in the textbook. It says a function f is increasing on an open interval. Notice we had the little parentheses there. If for any choices of two values of x, and it says x1 is less than x2. That means as you're moving from left to right, the x values are getting bigger. x1 is less than x2. Okay, so as you move from left to right, the x's are getting bigger. It's increasing as long as the y values for those x's are also getting bigger. The y value at x of 1 is less than the y value at x of 2. Do you see how the definition looks hard, but that's all it's saying is, this says as the x values increase, x1 is less than x2. The y values increase. The value at x1 is less than the value at x2. Okay, everybody see it? And the function decreases on the open interval. We still have the x values increasing. x1 is less than x2. You're looking from right to left to right, left to right. The x values are increasing, and it's decreasing if the first y value is greater than the second y value. The y value at x1, the y value at x2, smaller, so it's decreasing. And my example didn't have a constant function in there, but everybody knows what a constant function is. The y value is not changing or going up or down. It's for all choices of x, the y values stay the same. Okay, so it's pretty easy to look at the graph. Now the next terms that we want to look at, and that's in objective 4, is the words local maximum and local minimum. And I wrote over in the margin of my book because many calculus books are going to call them relative maximums and relative minimums. And I will probably use the word relative quite a bit. All right, now let's just use common sense, and then we're going to go back to what the book says. Notice there's a little calculus symbol here, so you know that's very important for calculus. All right, we're going to go first with common sense on my graph. Where do you think I have a local maximum point? Where do you think I have some local max?
The high
It's 2 and 2, or negative 2 and 2.
Okay, it looks like that I have a little maximum point here, and it looks like I have a little maximum point here. Do you see any other
And
place else I might have a
5 and
little
0.
max?
5 and 0.
5.
Yeah. Okay. Now the word local, I'm going to help you remember this. Local, max, or relative. All right, I like to use the word local or relative to mean you got to have a little community. Your little local community or all your little relatives. You got to be part of a group. You got to be part of a group for there to be a local max or min. So I don't know if you saw how I put little parentheses here. You will have a local max or min if you can come in and do a little grouping around this, and this is your highest point. So anywhere you can go on the graph and put all your little friends around, your local community or your relatives, and you're the highest point there, that is going to be a maximum point. All right, let's look at the words in the book. The words in the book says, when the graph of a function is increasing to the left of x equals c and decreasing to the right. So whenever your graph goes from increasing to decreasing, you're going to have a max. So you got to be all around that little point. All right? And it says, then c is the value of, then at c, to the right of x equals c, then c is the value of f is largest. At c, the value of f is largest. The local max, this value is called the local max. Well, what I wanted to say was, generally you say, what are the relative or the local max? And it means values of the function. It asks for the values of the function. All right, we have points that are local max and mins, but when it says, what is your local maximum values? What would you say the local maximum values of the function are?
2, 4, and 0.
2 from right here, and 4 from here, and 0 from here. All right, so when I say, what is the relative maximum values? Relative maximum values, it means values of the function. What are the y values? Okay? It is clear these are relative maximum in points, but values of the functions are the y values. Everybody got it? Okay, now let's do, I'll do purple. Ooh, let's do green. Where do you think the local mins are? Local minimum points. Okay, around here. And you got local, so you got to go to the little neighborhoods. Where else do you see a little local?
Negative.
Minus,
Yeah.
negative.
Right here? Okay, so let's go back to the definition of the book. I want you to realize this book is very readable. When the graph of a function is decreasing to the left of x equals c and is increasing to the right of x equals c. So decreasing to increasing. Do you see? Decreasing to increasing. You're going to have a local min. Okay? You got to be on both sides of x equals c. All right, so that's exactly what you guys said. This is decreasing to increasing. This is decreasing to increasing. So, if the question says, what is the local or relative minimum values? And your book just says local minimum values or local mins, but it means values of the function. All right, so what are your local minimum values? It's kind of hard to tell. What would you guess that is? It's like negative 1/2, right? And what else? Negative 2. All right, so our local minimum values are negative 1/2 and negative 2. And I didn't record the local maxes. The local max values are 2, 4, and 0. Everybody got it? All right, now your book does not ask this question, but it is asked in calculus. So I want to tell you you can use your common sense, and you got it. If I said to you, what is the absolute maximum value of this function? The absolute maximum value of this function, what would you say?
4.
4. Because 4 is absolutely the biggest y value there is. Okay? So in calculus, sometimes you'll be asked, what is the absolute maximum value of this function? All right, so you could have an absolute here. You can also have an absolute at an endpoint, but you can worry about that in calculus. All right, suppose this question says, what is the absolute minimum value of this function? What would you say? Right, well, and negative infinity doesn't exist, so you'd have to say there isn't an absolute minimum value because the graph goes down forever and ever and ever. Everybody good? All right. I almost believe that takes care of those words. The next thing we want to talk about is average rate of change. Average rate of change. That's in this section. Let me put this right here. Average rate of change. And I decided to make up a little story so it'd be more fun to do the problem. You're on a trip. Okay, we're talking about, this is objective 6, finding the average rate of change of a function. You're on a trip, and along the x-axis, we have hours you're on your trip. You're driving your car. And along the y-axis, we have the number of miles that we've covered. Okay? So we start out at 0, 0 because we start out at 0 hours. This is distance from home, wherever our starting place is. And at the end of 1 hour, we look at our little odometer on the car, and we've gone 50 miles. At the end of 2 hours, looks like we've gone 75 miles. Put a little 75 right there. And at the end of 3 hours, it looks like we're at 150 miles. And at the end of 4 hours, 150 miles. So we just plotted some points at the end of each hour to see where we were. Okay? I would claim that at the end of 3 hours, we stopped to eat. Because you haven't covered any distance between 3 and 4 hours. Okay? Alrighty. Average rate of change. Average rate of change is really no more than the slope of the secant line. Slope of the secant line, and we know that the slope of the secant line is just the slope between 2 points. Okay, slope of the secant line. All right, let's pretend that you've gone to visit your parents, and you arrive after 4 hours. And so your mom says, okay, you just traveled 150. We're going to claim that they hit around the block and sat there for an hour. Okay. All right, so it took you 4 hours to get home for you to finally get in the door, and your mom is immediately going to go, okay, you traveled 150 miles in 4 hours. I want to know what kind of speed you went on the highway. All right, so we're going to find the average rate of change between t equals 0 and t equal to 4. So at t equal to 0, remember your y value here is 0, so our slope will be, our points are at 0, 0, and 4, 150. So basically we're looking at the slope, whoops, if I can draw it, slope of that line right there. Okay, that's the slope of the secant line between those 2 points. So we'll have 150, difference in the y's, minus 0, over the difference in the x's, 4 minus 0. Now let's put units with this so we'll have some meaning. We want to be able to interpret what we're saying. The y values represent miles. The x values here represent hours. And so 150 divided by 4, I should be able to do this in my head, but all of you are staring at me, so I can't. 37.5. 37.5 miles per hour. Is your parents going to be happy that you took a nice 4 hours to only get there 150 miles? You're going to go, I only averaged 37.5 miles per hour. I was a very careful driver. But would you say that was the whole story?
No.
No. Let's see how this person did between hour 2 and hour 3. All right, that's an average rate of change. You know, if this person is driving along here and they look down at their speedometer, they're probably speeding. That is called instantaneous rate of change. That is the speed at that very moment. Okay, that's the speed at that very moment. But we're looking at over a period of time, and that gives me average rate of change. All right, let's find the average rate of change between t equal 2 and t equal to 3. It's a good thing the mom didn't say, well, what about between hour 2 and 3? What was your average rate of change? All right, t equal 2, we have 75. This is the point 275. And at 3, we have the point 3, 150. Okay, we wouldn't be making mama so happy here. The slope is 150 minus 75 over 3 minus 2. And let's don't forget that's miles divided by hours. Everybody know where I'm getting my units from?
Yeah.
The y value is the miles. The x-axis is the hours. 150 minus 75 is 75 over 1. So between the second and the third hour, the average rate of change, the average speed out on the highway was 75 miles per hour. Okay? Everybody got average rate of change? Average rate of change is no more than the slope of the secant line between 2 points. Let me go to the book and just show you this. This is on page 233. Average rate of change is the change in y over change in x. Difference in the y values over the difference in the x values. All right. Are we good, everyone? All right, let's go to the exercises. Also, by the way, on page 235, that's, again, where they talk about it being the secant line. The average rate of change of a function has an important geometric interpretation. We label 2 points, and this is the slope of the secant line. So the theorem is the slope of the secant line, the average rate of change of a function equals the slope of the secant line containing the 2 points. I just jumped right to the calculus related. Okay? All right, let's work a couple examples directly from the exercises. And we're going to jump on problem number 54, page 238. problem 54. Okay, now the other examples in the back of the book, we've already done very similar problems to increasing, decreasing, local max, mins. My example, I think, covered that. All right, question number 54. It says, find the average rate of change of this function from 0 to 2, 1 to 3, etc., etc. Okay. All right. This is saying you don't have a picture of the graph. Could you figure out how to do this? Yeah. All right. Let's first do it without the picture, and then I have drawn the picture. Everybody got the question? We'll just do one of these. Let's just do B, 1 to 3. F of x equals negative x cubed plus 1. We're going to find the average rate from x equal 1 to x equal to 3. All right. We're going to do it without the picture. All right, so this is my function, and if I want the average rate of change. All right, let's verbalize it so you never forget. Average rate of change is just what? Slope of the line between those 2 points. Yes, which is slope, which is change in y's over change in x's. And recall that y is your function of x. All right, so when x is 1, what is the y value? When x is 1, what's the y value? 0.
Yeah.
Remember, you cube your 1 and then you take the minus because there's not parentheses there. So it's really like minus with the 1 cubed plus 1 or 0. Okay, when x is equal to 3, we have y equals minus, and then you're going to cube your 3 and add 1. Okay, remember minus in front of the x cubed. Without parentheses, the x is cubed and then the minus. Some people miss that on tests. Okay, 3 cubed is 27, and then we got a minus 27. Plus 1, and we got negative 26. All right, so average rate of change, the difference in the y values, minus 26 minus 0. Minus 26 minus 0. What goes in the denominator? Difference in the y's over
3 minus
3 minus 1. Difference in the x's. Negative 26 over 2, and that looks like a slope of 13 average rate of change. All right, that's kind of a boring question because it doesn't have any words to go to it. You go, who cares? All right, I drew the picture for you on Maple just so you can see what it looks like. And when x is equal to 1, here's the y value right here. And you'd already figured out that that was at 0. And when x is equal to 3, x is equal to 3. Oops. It looks like somewhere right here. If you make your dot big enough, I'm bound to hit it. All right, and that comes over to, see? Perfect. Negative 26. And we found it to be negative 26. And so this 13 is really the slope of this line that passes through those 2 points. Everybody good? Okay, well, let's get off that because those aren't very exciting. Let's go to a word problem on page 239. Page 239, and we're going to look at problem number 64. Okay. These are very calculus-related exercises here. In calculus, you're going to be working with boxes to maximize volumes, minimize surface areas, and so in pre-calculus, you want to learn how to set all this up and be good at it. Okay, so we're going to, in number 64, we're going to construct an open box. We have an open box with a square base. And we want this box to have a volume of 10 cubic feet. All right, so let's first draw our box. We have a box with no top. It's important that you catch those words. Open, no top. Square base box. And volume means how much does my box hold. Okay, so let's draw it. This is number 64. All right, everybody has their own little ways of drawing boxes. I just make two little squares. Ooh, that's not going to look like a square base, but you can just pretend that the camera's bad.
Okay.
Not me, but the camera. Okay.
Okay. Sure.
All right, so if this is my box and it has a square base, that means the bottom is a square, and it says to use the square base as x's. So we're going to label this to be an x by x. All right, that's a square base in case you can't tell. Now I don't look like I'm convincing you. All right, and I'm just going to call this h for height of my box. Can you visualize your box? All right, now let's translate some of this. This particular box with a square base is to have a volume of 10 cubic feet. This is x feet, height is h feet. Okay, we're told that we're only interested in a box that has a volume of 10 cubic feet. All right, how do you find the volume of a box? What is that formula? All right, it's basically taking the area of the bottom and multiplying times the height, right? Anything that goes straight up and you want to find the volume of it, you just get the area of the bottom and multiply it times the height. So in our case, length is x, width is x, height is h. So we have x squared h is equal to 10. So this represents a formula that represents the volume of our box. Okay, now we're ready to go to the question. All right, we want to express the amount A of material used to make such a box, the amount of material as a function of the length of a side of the box. All right, so we call the amount of material, that's the cardboard that your box is made out of. So really what we're looking for, I'm just going to use SA for surface area. Surface, that you're going to call it surface area in calculus. Surface area. SA, surface area. We want surface area defined in terms of x. All right, so we're going to start out writing in words the parts of the cardboard that make up this box. You need cardboard on the bottom, so we're going to need the area of the bottom. And then, doesn't our cardboard box have a front face and a back face? Okay, we need the area of the front and back face. All right, so you have your front part here and your back part. Do you see that on your box? Okay, and then we have the two sides of our boxes. So we got plus the area of the two sides. All right. So many times when you tackle one of these word problems, if you'll verbalize what you're looking for, then it's going to be easier to work with. So we want to find a way to express the amount of materials. That's called surface area. The amount of materials used to find this box when the length of a side of the square is x. Okay? Alrighty, so let's see what we can do here. I'll try to color it in. What is the area of the bottom of my box? X times x, right? It's just a flat old rectangle, which happens to be a square. So the area of the bottom is x squared. All right, let's go to my front face. My front face is right here, and my back face is right here. So what is this area where the purple is?
XH.
Okay, I have one XH for the front.
And
Does everybody see
2
that?
XH
X
for
by
the back.
H. And I have another XH for the back. So the area of my front face and back face is
2HX.
2 times XH. Everybody see it? All right, now let's go to the sides of my box. Sides of my box are going to be in blue. Let's do orange. Okay, orange. All right, here's the sides of my box. So what is the area of this side right here?
XH.
X times H, it's a rectangle. And I have it over here also. So I have plus 2 times XH. And that worked that way because I had a square base that these two are going to look alike. All right, so now let's clean this up. My formula for surface area is x squared. 2xh plus 2xh is 4xh, surface area. All right, let's see if we've answered the question. Express the surface area in terms of x, such that the box is a function of x. Have I expressed surface area as a function of x only? Do you only see x's over here? No, it's got an h in there. All right. This part right here is really called a constraint equation. It's called a constraint equation. What happens is this surface area is a general formula for every box with a square base with no top. But we want the particular box that will hold 10 cubic feet. So how can I use my constraint equation to get this only in terms of x? How can I use my constraint equation to get this only in terms of x?
Solve for X with the
Solve for h up here, right? H
Oh,
is
you wanna do
10 over x squared,
and then substitute.
and then make a substitution right here. Okay, so our surface area, which is part A of our question, is the surface area defined only in terms of that square base, but with the restriction that it's going to hold 10 cubic. Let me write it right here. X squared plus 4x times 10 over x squared, making the substitution. That simplifies to x squared. And then 4 times 10 is 40. And this 1x divided out with one of the x's in the denominator. And so I get 40 over x. So this is the formula for the surface area of this box that will hold 10 cubic feet. Does that make sense, everybody? Are you good? Okay, let's go to part B. Part B says, how much material is required? How much material would be required? And A represents the total amount of material for a base that is 1 foot by 1 foot. When x is 1, how much material is required? What would you do?
Substitute 1 for X.
Yeah, you just substitute 1 for x. Let me flip the page. B, I'll rewrite surface area is equal to x squared plus 40 over x. Okay, so part B says when that base, x, when the base is 1 foot by 1 foot, how much surface area? And this is, what's my units going to be for surface area?
Feet squared.
Square feet, yes. So I'll have 1 square plus 40 over 1, which is equal to 41 square feet. See, x is feet, so you got square feet, surface area. B, C. How much material is required if the base is 2 feet? So aren't we just going to put a 2 in for x? Okay, so we'll have 2 squared plus 40 over 2. 4 plus 20, it will take 24 square feet. if I were in the business of making boxes, I would prefer a box that had a base with 2 square feet over a base with 1 square foot. Why?
Because it's less surface area.
It's going to take
Cheaper.
less surface area. It's going to cost me less to make the box, isn't it? All right. What I have graphed here using Maple is this function x squared plus 40 over x. I've graphed this. And along this axis is the dimensions of the base. X, if it's 1 square foot, we found the surface area to be 41. So when x was 1, right here is perfectly the surface area is 41. When x was 2, coming up from 2, the surface area was 24. We found out exactly what it was. Okay, so if you're running a business and you've got to ship out 10 cubic feet and you got to build the box, you want to have a box that has the least amount of surface area because you're paying for the materials. So that's why you need math before you go out in the real world working. Okay, so let's look at this graph and decide what the dimensions of the base of the box should be so that you use the least amount of materials, which in turn makes us have the least amount of cost to our business. Okay, so where are you going to find the minimum value of the function here? Minimum value? Looks like somewhere right in this range. Okay, we can't see it exactly. You can use calculus or you've got your little graphing calculator there to trace it. But somewhere, it looks like 2.2, 2.4 to 2.6, somewhere between 2.4 and about 2.6 for the dimensions of your base, 2.4 by 2.4, 2.6. You could try those out. That is going to minimize your surface area, therefore costing you a lesser amount of All right, everybody good on that? Okay, I think that pretty much covers 2.4. Let's just make sure we got it all in here. And then we're going to move into section 2.5. All right. We know how to tell if a graph is increasing, right, decreasing, or constant. Remember, you're always looking as x gets bigger. You're always looking from left to right, and you're looking at those y values. Local or relative max. Remember, you have to go in that little neighborhood and find your highest point for a local max. Or go in that little neighborhood and find your smallest point for a local min. But when it asks you for the maximum or minimum value of the function, what kind of answer are you giving? The y value. That is the value of the function. Okay. Average rate of change, what's that, everybody? Just the slope of the secant line. Okay. And we only did objectives 3, 4, and 6. That's all that's required for this class. Let me just flip the pages and make sure we got everything covered. There was a warning at the top of page 231 that I had highlighted in yellow. It says, we describe the behavior of a graph in terms of the x values. So when you're saying over what interval is the function increasing, it means over what domain, over what values of x do the y values go up. Okay? All right. And as I turn the pages, it looks like to me that I have covered it. All righty. We are ready for section 2.5. Let's go back and see what we were going to cover in section 2.5. This one should be a piece of cake because you have grown up on linear functions. You have grown up on linear functions. We want to graph a linear function. What will that take you? 5 seconds. All righty. I'll push it to 10. I'll double it, okay? All right, then we want to look at applications. And we're going to look at 3 applications in here of a linear function. or maybe 2 applications, and then we're going to do a direct variation. Let me see, 1, 2, yeah. We're going to look at 2 applications of linear functions, and then we're going to jump on direct variations. And distinguish between linear and nonlinear relations. That's another 5-second question. Okay? Alrighty, let's go to preparing for the section. We're on page 249. We got to be ready before we can start. We're on page 249. And let's see. We'll do it in reverse order this time in case you think you guys got the hard one last time. You get number 1 question, you get number 2, you get number 3, and you get number 4. Okay? Y'all are 4. Preparing for the section. We're on page 249. Was y'all's question too easy? Do you mind if I put it on the camera so I don't have to rewrite it? Do you have it written where I just put it on the camera without me rewriting it? Okay. Okay, will yours show up? Okay. If you'll write it where I can just put it on the camera, that'd be great.
You can use
I
her.
said 2/2.
Okay.
It's gonna be 1.
Alrighty. Don't go away.
What is that? 2/2. Okay.
This way we'll check your work on camera, and then if you made a mistake, that's going to help somebody who's watching this.
I hope I make a mistake.
You hope you made a mistake so you'll learn. You're good.
So, what we just found would be a y-intercept, right? So that means
That's what I find another point, right?
negative 3x plus 8/3.
If x is 2 over 10 y negative 3, that's
Then
the
we
first
put
one.
Not doing that one.
That's later the thing. But you don't really have to do that because it's 3 that way.
Do you have a graph that I can use on camera?
No, I don't.
Do you want us to make a graph?
Okay, I'm going to push you. Let's answer some questions about this.
You can just like zoom in on the calculator.
All right, this is from section 2.5. And we're supposed to graph y equals 2x minus 3. First of all, I want everybody in unison to tell me what this is going to be the graph of.
A line.
A straight line. Graph of a straight line. How do you know?
Because it's the x has a
Exponent.
of 1.
And the,
Y has an exponent of 1.
okay, because the exponent on x is 1, and the exponent on y is 1. So anytime you have an x to the first and a y to the first and no other x's and y's in there, you've got a straight line. So you know it's a straight line. And then this is your favorite form of the line, right? You like y equals mx plus b. So this is called what form? Slope intercept. And the b is which intercept?
What?
The y-intercept. So you knew immediately that -3 is the y-intercept. You can always let x be 0, and you immediately see y is -3. Okay, slope is rise over run. Slope is rise, change in y, change in x. So if we know one point, to get to another point, all we have to do is do what? Go up 2 and over 1. And so the next point that should be on the line is 1, -1. What's the next point that should be on the line? Up 2 over 1 should be 2, 1. How can I check to make sure I didn't mess up with my counting?
You just put a ruler against it.
Plug and chug back into the equation. When you let x be 2, is the y value going to be 1? 2 times 2 is 4. 4 minus 3 is 1. Check.
Yeah.
X is 1. 2 minus 3 is -1. Check. Okay. So now all you have to do is connect the dots. Try to do them as straight as you can. If it doesn't look straight, it's the camera's fault. Okay, there we have the graph. How'd your graphs look? Good? Yours didn't look good? What'd you do wrong?
I have no idea.
Did you use the form to do your slopes, or were you just trying to pick some points?
I was trying to plug in like different numbers to be able to get like in that same equation that they've given, right? I was putting in my own numbers to get 2 different points.
Okay, you can do that. That's a little bit more time consuming. You just said probably let x be what number?
I had a 0 and I had a 2.
A 0 and a 2? Okay, so when you let x be 0, your y value was -3. When you let x be 2, your y value was 1, and you plotted and your line went straight through there. That's perfectly fine. This particular section of and there's nothing wrong with that, so you're perfect. Just want you to know that. All right, but this particular section of the book is hoping that you're going to recognize y written in terms of x and using the slope-intercept form. Okay, we're good. Everybody good on this? All right, now for number 2, I have this written. Find the slope of the line joining the 2 points. Do you care if I write on your paper? No. Okay, the 2 points are 2, 5 and -1, 3. And so slope is equal to your change in y's over your change in x's. Alrighty, so let's see. You did your y values, 5 minus 3 over 2 minus a -1. 5 minus 3 is 2. 2 minus a -1 is 3. And everybody would like to say that is perfect. And you had wanted to make a mistake so you'd learn from your mistakes. Too bad. You got it perfect. Okay, you got problem number 3 for me?
Hopefully we did it right. I think we did good.
Here, we pass that back. Just think your work will live on for years with these tapes. Okay, number 3. You don't mind if I write on yours? Okay, number 3. Number 3 says, find the equation of a line. The slope is -3, and it passes through the point -1, 5. Okay, so you had lots of ways you could do this, and it looks like to me you chose to...
So if the slope was -3, and then 0 minus 5 would be -5, and then x minus 1 would be the change in x.
Where'd you get a 0?
It'd be the y-intercept.
We don't know anything about the y-intercept.
Yeah, but if you know the y-intercept, then the y would have to be... No, wait, the y wouldn't have to be... The x would be 0. So we did it backwards.
Think you might have done it backwards?
Yeah, because the x would be 0, so it would be x minus 5 over -1.
Okay, we're going to come back and talk to you in just a second. All right, if you know a slope and a point, do you know how to write one form of an equation of a line real fast?
Yeah,
What is
slope.
point slope? Point slope
I
form,
hate slope forms, but that's okay.
which is y minus the y coordinate equals the slope times x minus the x coordinate, which is what you were trying to do here by solving for m. I'm going to go up here now. You wanted to do m equals y minus y1 over x minus x1. So I'm going to go back to yours in just a second. All right, you could go directly to the equation of the line, so it would be y minus the y coordinate equals the slope times x minus the x coordinate, right? So an equation of the line could be y minus 5 equals negative 3 times x plus 1. That's a perfectly good equation of a line. It looks like you were going to slope-intercept form. Well, that's not going to be any problem to get to because all you have to do is solve this for y. Slope-intercept. So we have y equals minus 3 times x plus 1 plus 5 minus 3x minus 3 plus 5, and you get minus 3x plus 2. So if you wanted to go to slope-intercept, it should be here. All right, so where did you say you went wrong?
Said that we did it backwards.
Okay, so you should have, if you were going to do your method up here, you would have had the slope, negative 3 equals y minus 5 over x plus 1. X minus a negative 1. Okay? All right, and then when you cross multiplied or multiplied through by x plus 1, you would have been right here.
But can't you say that the x would equal 0?
You can't say that x is 0 because you don't know the y-intercept. You
But
only
the
know
y-intercept x would have to be 0 because the y-axis passed through x0.
you don't know it passes. It's somewhere it is going to cross the y-axis, but you don't know where it is at this moment.
That's why.
The y-intercept is at positive 2.
Yeah, but if the x has to be 0 for the y-intercept to actually happen.
Right.
So you can't just say that the x is 0?
No. If you're solving for y, once you get this far, you could, but at the moment that you were starting the problem, you didn't know enough. You would have too many unknowns if you tried to do that. If you're trying to make x be 0, you got a y up here. Is that what you're saying?
Yeah.
So you make x equals 0, so you have negative 3. All right, so let's see what you were doing. Negative 3 equals y minus 5 over negative 1. So 3 equals y minus 5. Y is equal to 8. Don't y'all be listening to this. I'll talk to you later.
Apparently.
All right. This would have been your setup if you were trying to go with the slope form, or if you had remembered the slope-intercept form.
It works out fine on my paper.
Did I do the arithmetic wrong?
Yeah, because you said that y would, that would equal negative 1. It's supposed to be
Oh,
positive.
it's the positive 1.
And then it comes out as 2.
Okay. And you would have found your y-intercept.
Yeah.
Okay.
So
All right,
I'm not
let's.
crazy.
I made a mistake right here. It should have been
0 plus 1.
0 plus 1. Okay, then that would have been negative 3 equals y minus 5 over 0 plus 1. And you would have come out with your y-intercept as being 2. So you were going to jump directly to here. Okay. All right. Now I figured out what you were doing.
I'm not insane.
Excuse me?
I said I'm not insane.
Except you worked it wrong and you threw me. I was
Yeah.
not quite sure where you were headed.
I worked it wrong the first time.
Okay.
Because I did it backwards.
All right. I need everybody to remind me again, how do you recognize a linear function? This time I'm going to call it a linear function. That means I want to write it as y equals. How do you recognize a linear function? What's it going to look like? If it's going to give you the graph of a line. What's your formula? Y equals mx plus b. So in this section, we're talking about functions as opposed to just equations. So on page 241, graph of linear functions. Remember, we write y as a function of x. It's just going to be in the form y equals mx plus b. You were used to writing equations of lines in point-slope form, slope-intercept form, and general form. But if we want to call it a function, y expressed explicitly as a function of x, we would write it in this form. Okay? Alrighty, and I just realized that we are out of time because class is over. We're going to pick up with our applications in 2.5 in the next lesson, and then we'll move on into 2.6. Please be reading ahead so you'll have some idea what's going on. 2.6 is a fun section, and we'll be doing a lot of graphs, so get ready. Yes?
How does the web assignments work out?
The web assignments are by the section, and you have some padding for the due date so that you can be working all along to go. You get like 10 or 20 submissions to earn a perfect score.
Like
When are each one of them due by? Is that due dates on there?
Okay, the due dates are on WebAssign to tell you the exact time that they're due.
Okay.
Okay? All right, have a great day, everybody.